All right, it's May 2014, paper number 3, problem number 2. Given two functions, we want to find their derivatives first. This part's pretty easy. F of x is ln x quantity squared. So we just use the chain rule. The derivative will equal, power down, 2 ln x, decrease the power, times the derivative of the inside. The derivative of ln x is 1 over x, so there we go. That's done. Part II, the derivative of g of x. Well, it's just about as easy, except g of x is defined as ln of f of x, so it's the ln of x quantity squared. So let's put some square brackets in there. So that derivative, start on the outside, the derivative of ln is 1 over, so it's going to be 1 over the quantity of ln of x squared. Now let's move to the inside. Well, we already did the derivative of that. That's part I, Roman numeral 1. So we just rewrite that as 2 ln x over x. We can do a little cancellation. We have ln x in the numerator on the second fraction and ln x squared. So we can cancel one of those. So we're going to end up with 2 over x times the quantity ln x. So that's done. Part 3. Hence, show that g of x is increasing on the interval from 1 to infinity, non-inclusive on the 1. Reason is you can't have the ln of 1 in the denominator. ln of 1 is 0, so you can't have that 0 in the denominator. So how do we show that g of x is increasing? Well, we just found its derivative. Here's the derivative of g of x. And that's going to be increasing because we can say g prime of x is greater than 0 for all x in the interval 1 to infinity. That's always going to be positive because 2 is positive, x has to be positive from 1 to infinity, and ln of x is positive. Therefore, g prime of x is increasing. Exclamation point. Okay, so part 2a is done. All right, let's move on to part B of problem 2. It gets a little harder. We're given a differential equation. Now, when you first look at it, hopefully you would recognize that as the integrating factor form almost. Because integrating factor form, you always have a derivative and then a function of x, and this is right off your formula sheet, by the way. Function of x times y. Okay, we've got a function of x times y. We've got the derivative, and then equal to some function of x, which they call q of x. Well, it's almost in that form except for the ln x out front. Well, to put it in integrating factor form, what we can do is take that and just divide through by ln x. So we end up with dy dx plus 2 over x ln x times y equals 2x minus 1. Again, dividing through by ln x divided by another ln x would be ln x squared. All right, now it's in integrating factor form. So what we have to do is find the integrating factor. Remember, the integrating factor is e to the integral of the function of x, which is right before the y. So in the general form, it's the p of x, and that's on your formula sheet too. Let me write that down. That's the integrating factor. So let's plug that in this specific case. So p of x is going to be this, which is 2 over x ln x. 2 over x ln x. Well, hopefully that kind of looks familiar because that's from part A. So let's go back. 2 over x ln x, scrolling back up slowly. That's the yellow highlighted one. So what that was the derivative of g of x. So if we go backwards, the integral of that is going to be g of x. So the results of e to the integral of 2 over ln x is going to be e to the ln of x quantity squared. Okay, so we're making progress, almost have that integrating factor. Well, e to the ln of anything is just that thing, so this result, e to the ln of x quantity squared, is simply ln of x quantity squared. Now that's our integrating factor. Now the next process in finding the general solution of that differential equation is to multiply through by the integrating factor. Okay, so we're just going to go back up to the form, let me highlight it here, this one. That's the differential equation after I divided through by ln of x. And I'm going to multiply that yellow one by ln of x quantity squared. And I'll put it down here. So ln of x quantity squared times dy dx plus 2x ln x times integrating factor ln of x quantity squared times the y equals the right hand side, which is 2x minus 1 over ln x squared, but we're multiplying by ln x squared, so the ln x squared, the denominator, cancels out, so you just get 2x minus 1. Okay, so after we multiply through by the integrating factor, we're ready to integrate both sides of this thing. Now remember, the trick on the integrating factor and then integrating both sides is the left-hand side is always the result of y times the integrating factor. And you can always check that. So the left-hand side, when you integrate that, you're going to get y times the integrating factor. Okay, so if you took the derivative of that, and to go backwards to check, first is y, derivative of the second, ln of x squared. And remember, y is, where did y go? There it is. Y times the derivative of the second, that's this, and then the second, ln x squared is that, times the derivative of the first is dy dx is that, so it checks. So we integrated the left-hand side, now we have to integrate the right-hand side, which is much easier. 2x minus 1 is increase over increase, so it's x squared over 2, but the 2's cancel, minus x, and then plus c. Okay, almost there. Find the general solution in the form of y equals h of x. So all we have to do is take this result and solve for y, divide both sides by ln x quantity squared, so we get x squared minus x plus c all over ln of x quantity squared. So finally, part 1 is done. Now part 2 is just a continuation. What they're going to have you do is solve for c. So it says show that the particular solution passing through the point with coordinates e comma e squared is given by. So what we're going to do is take our result, scroll up a little bit, take this last result of the solving the differential equation, and we're going to plug in for y, we're going to plug in e squared, and for x we're going to plug in e. So we have e squared minus e plus c all over ln of e quantity squared. Well, the right-hand side, what we have on the denominator, ln of e is 1 squared is 1, so this becomes e squared equals e squared minus e plus c. The e squareds cancel on both sides, so we have 0 equals negative e plus c, and therefore c equals e. So we take our c value, plug it back in up here, and our particular solution is y equals x squared minus x plus e over ln of x quantity squared. Exactly what they wanted us to get. That wasn't too bad at all. And finally, the last part, sketch the graph of your solution for x greater than 1, clearly indicating any asymptotes, any max or mins. Well, remember, this is paper 3, therefore it's calculator friendly, so what I would suggest is just take that circled result right there go to your calculator, plug it in, play with the window a little bit. You know, I think this function, oh, well, it says x greater than 1, so set your window from 0 to 10 maybe. And you can also think about this a little bit. Asymptotes, what's going to make that denominator equal 0? That's where it'll be asymptotic. So, well, you know, if x is 1, the ln of 1 is 0. So, and your calculator will confirm this. You'll have an asymptote at 1. Then if you just sketch this, you'll see the graph looks something like this. And all it's saying is clearly indicating the asymptotes, so you can just say x equals 1. And any max or mins, well, you can see there is a min, there is a turning point, and all you have to do is use your calculator, the built-in function, to find the minimum, and it turns out to be 3.137.21. And we'll just call that a min. And that's pretty much done. As long as you label those things, you can use your calculator to get that final answer. And that is the end of the 17-mark problem. Problem number 2. Done.